section, we have Dr. Binitha NN, Assistant Professor, Department of Chemistry, SNGS College, Pattambi, and recipient of Young Scientist Award, EFCS 2020. She had more than 67 publications in reputed journals and approved research grade of University of Calicut, the recipient of UGC Research Award. And her area of research interests include green chemistry, nanotechnology, heterogeneous catalysis, photocatalysis, and alternate fuels. On behalf of EFCS 2020 and every participants, I would like to welcome Dr. Binitha ma'am to deliver the talk on green graphene nanocomposites for versatile application. Ma'am, please.
Thank you. Good afternoon. First of all, let me thank you once again for the organizers of this program for giving me an opportunity to be here. I think we can start. Let me share the screen. Hello.
Dr. Binitha, it is coming.
Can you see my screen? No.
Yes.
No, ma'am.
Just a second. Is the screen visible?
Not yet.
No, madam.
No, ma'am.
Is the screen visible to you?
Yes,
Okay,
ma'am.
no,
Yes,
fine.
ma'am.
Okay. Thank you all. Let me start. The topic of the presentation is green graphene nanocomposites for versatile applications. We all know that graphene is a green material, and here our emphasis is on the production of graphene via green methods. All of us know about graphene. I just introduce for those who are new to this topic. Graphene is a wonder material. It is a 2D allotrope of carbon. It has fascinating properties such as size, high surface area, very high conductivity, tunable optical properties. It is a biocompatible material. It has high thermal as well as chemical stability and has high mechanical strength. These properties make it suitable for the applications such as in biological applications, in supercapacitors, sensors, electronics, energy devices, for ultrafiltration, catalysis, etc. And the composites of graphene have synergistic properties that are not attainable by the individual components. There are lots of methods available for the production of graphene. Both top-down as well as bottom-up approaches are generally used. In the top-down approaches, we start from graphite, and by various means such as exfoliation, both mechanical exfoliation, liquid phase exfoliation, etc., we are producing graphene. And another method, various species are intercalated between the graphitic layers, and further exfoliation is very easy. And from Graphite by electric discharge, by electrochemical methods also, we can produce graphene. And in the bottom-up method, chemical vapor deposition, silicon carbide heating, etc. produce high-quality graphene networks. But these methods are comparatively costly. Heating of solid carbon sources such as glucose in an inert atmosphere can produce graphene, and unzipping of carbon nanotubes can also result in the formation of graphene. But the large scale as well as commercial production of graphene is dependent on the reduction of graphene oxide. Different oxidation methods are there for the production of graphite oxide from graphite, and the most common method is Hammer's method. We all know that graphite is a hydrophobic material, and initially for the production of graphite oxide, graphite is subjected to drastic oxidizing conditions using KMnO4, concentrated nitric acid, concentration sulfuric acid, NaNO3, etc. And as a resultant, graphite oxide is produced. Graphite oxide contains various functionalities such as epoxy, hydroxy, carbonate, carboxyl, etc. And as a result, the layer distance of graphite is enhanced. In addition, the material can incorporate polar solvents and it becomes hydrophilic in nature. And by ultrasonication, these graphite oxide layers are separated to form graphene oxide. And for the production of graphene, this graphene oxide is then reduced by various means. And we are getting graphene, and usually we call that graphene as reduced graphene oxide, because some of the functionalities remains there. And in addition, there are lots of defects on this reduced graphene oxide. So the conductivity and the regain of aromatic network is not so possible in reduced graphene oxide. But the functionalities of reduced graphene oxide allows the incorporation of various species between the graphene layers. These are the photographs during the preparation of graphite oxide. We are using concentrated sulfuric acid, graphite, KMnO4, NaNO3, etc. And it's a time-consuming process. Even though we are conducting the experiment at low temperatures, there are lots of fumes evolving during the experiment. So it is not a green method. So we prefer the preparation of graphene via green techniques, and that's why we call it as green graphene. The limitations of graphite oxide assisted methods are the hazardous conditions we are using during preparation and the possibility of contamination. Many graphene oxides possess manganese as one of the contaminants. We are using KMnO4 during the preparation.
Carry on.
Chemistry. Graphene can be used for versatile applications, as we mentioned earlier. But when we use graphene for applications, specifically for pollutant remediation and in biological applications, these graphene should not be contaminated. Graphene can be used for pollutant remediation by processes such as photocatalysis, and graphene can be used for the filtration, for ultrafiltration for the purification of water. And graphene in biological applications, it is used as biosensors, antibacterial agents, and various applications are there, including drug delivery. So that graphene should be highly pure, and it may not be contaminated with metals like manganese. Another demerits of graphene oxide is that there should be always defects on the graphene sheets produced via graphene oxide assisted methods. And the process is time consuming and laborious, and sometimes the thickness control is not so possible in graphene oxide. Still, we are getting sometimes monolayered graphene, but from my point of view, one of the major limitation of this graphene oxide is its low thermal stability due to the presence of various functionalities as well as defects as well as holes on graphene sheets. It decomposes about 200 degrees Celsius, and thus graphene cannot be used for graphene derived from graphene oxide cannot be used for high temperature applications. For example, for the conversion of plastics to fuels, for cracking reactions, etc., it cannot be used. So we here prefer the production of graphene via some green methods. But these green methods should be cost-effective, and easily performable. And there are lots of methods available for the production of graphene. And here I present some of the liquid phase exfoliation methods for the production of graphene. Graphite can be exfoliated using various solvents, and graphene oxide can be produced by not graphene oxide. The pure graphene can be produced by ultrasonication, but the solvents here usually we use are toxic NMP, N-methyl pyridone, DMF, dichlorobenzene, etc. These are not so green methods, and it again questions the use of green graphene for applications such as pollutant treatment, biological applications, etc. Another way is to incorporate different species between the graphitic layers and further exfoliation. Surfactants can be incorporated between the graphitic layers because surfactants possess both hydrophobic ends as well as hydrophilic ends. So surfactants can be incorporated between the layers and it can be exfoliated. Graphitic layers can be exfoliated using green solvents such as water and alcohols. This is the advantage, but the disadvantage is that the surfactant removal is not so easy and it also can cause contamination. But here we use a perfectly green material, ethyl cellulose, for the exfoliation of graphitic layers to graphene. Ethyl cellulose is a green material. It is a derivative of cellulose in which some of the hydroxyl groups on the repeating glucose units are converted into ethyl ether groups. And it is a non-toxic material and it is hydrophobic in nature. So it can be easily incorporated between the graphitic layers. Additionally, it is already used in various applications, including as food additive. So the material is a perfectly green material. It is also used for controlled drug release formulations. So it is already applied in biological applications. In addition, it have many other applications. So here we prefer the use of ethyl cellulose for the exfoliation of graphite. And about nanocomposites of graphene. Graphene can form nanocomposites with various species, including metals, metal oxides, etc. And these nanocomposites have synergistic properties unattainable by the individual components. Usually, graphene-based nanocomposites are prepared using graphene oxide assisted methods. This is because of the lots of functionalities available on graphene, and it can successfully incorporate different species on it by covalent binding as well as polar interaction, etc. But if we are using a graphene sheet prepared by other methods, we are getting a perfectly aromatic conjugative network, and there is no defects or functionalities on the sheets, and the electron mobility will be very high, but all metal oxides cannot form strong composites with this pristine graphene. Some metal oxides such as Fe2O3 succeeds to form stable nanocomposites with a perfectly pristine graphene, but in other cases such as with the titanium dioxide, etc., if we are using graphene prepared by other methods, the composite is not so stable. Some of the metal oxides leach out easily. But here, by using ethyl cellulose, in addition to exfoliation of graphite, this ethyl cellulose additionally leads to edge functionalization of graphene. These functionalities can help in the incorporation of metal oxides to it. So here we prefer the use of less toxic solvents for direct exfoliation of graphite, and we prefer the preparation under mild conditions with the use of surfactants or exfoliating agents. And here our exfoliating agent is ethyl cellulose, and we prefer the use of green solvents. And here we are using isopropyl alcohol for the exfoliation of graphite. Ethanol can also be used successfully. And for applications such as in electrochemical applications, the less defective graphene sheets having extended aromatic pi conjugative network is a desired property. And the formation of nanocomposites of graphene with metal oxides and as well as metal nanoparticles can additionally hinder the restacking of graphene layers back to graphite. And it can also additionally impact synergistic properties as already mentioned. So the objectives are preparation of graphene by ethyl cellulose assisted liquid phase exfoliation of graphite under mild conditions. We are using bath sonicator for the exfoliation of graphite. And here we present the composite of cobalt oxide with graphene. And the preparation is done by solvothermal method. The material is characterized by using few techniques just to find out the active centers responsible for the electrochemical activity. And we also investigated the electrocatalysis of 4-nitrophenol using the produced cobalt oxide graphene nanocomposite modified glassy carbon electrode. Directly to the experimental procedure, we just mixed ethyl cellulose and graphite in a specific ratio in isopropyl alcohol solution. The mixture is sonicated for 3 hours in a bath sonicator. We got stable graphene dispersion. The unexfoliated graphite is separated. By using exfoliating agents, normally we are getting highly concentrated graphene solution. It is just graphene dispersion. And to this, for the formation of cobalt oxide graphene nanocomposite, we add cobalt acetate dissolved in IPA. And during solvothermal treatment for the precipitation of cobalt oxide, we use urea. And after solvothermal treatment, the mixture is filtered, washed, dried, and calcined at 400 degrees Celsius. And we got cobalt oxide graphene nanocomposite. We can note that the calcination temperature is 400 degrees Celsius. This is to ensure the complete removal of ethyl cellulose, and we could successfully produce graphene nanocomposite if we are using a graphene oxide assisted method or graphene oxide based graphene. We cannot go for a temperature as high as 400 degrees Celsius at normal conditions. In those cases, we have to use inert atmosphere. And we have investigated the electrochemical application of the developed cobalt oxide graphene nanocomposites in the electrocatalysis of 4-nitrophenol. And modified glassy carbon electrode is used for studies. And platinum wire is the counter electrode, and AgAg cell is the reference electrode. We have investigated the electrocatalysis of 4-nitrophenol in 0.2 molar sulfuric acid. Here I would like to show you, we got a very uniform layer of cobalt oxide graphene nanocomposite over the glassy carbon electrode. About the results and discussion. First, we analyze the X-ray diffraction patterns of the nanocomposite. From the XRD patterns, it is clear that we are getting spinel CO3 offer as the cobalt oxide phase. And usually, it is not so widely reported for the highly crystalline CO3 offer graphene nanocomposites. In most cases, the CO3 offer spinel is found to be more or less amorphous in nature, but here, comparatively, we got well-defined peaks for the CO3 offer spinel. In addition, graphitic peak is also visible there, but it is not shifted towards left as in graphene oxide because there is no functionalities present in the surface of the graphene sheets, but the broadening of the peak suggests edge functionalization. And the functionalization is further proved from FTIR spectral analysis. The composite shows peaks specifically for CO3O4 aromatic CC stretching, and in addition, it confirms the functionalization of the nanocomposite by the peaks around 1000 centimeter raised to -1. It corresponds to COC as well as COH linkages, and the peak around 2900 centimeter raised to -1 indicates CH, aliphatic CH or carbonyl CH. A carbonyl peak is also visible around 1700 centimeter raised to -1. These peaks indicates the functionalization of graphene. Then we check the TEM images of the composite so as to confirm the formation of a stable nanocomposite. If the composite is not stable, we can see particles outside the sheets. But here, all the cobalt oxide particles are well-defined, well-dispersed in the graphene sheets. And the particle size is found to be in the size range of 5 to 15 nanometer, and the material is almost spherical in shape. The lattice fringes of CO3O4 is also visible from the TEM images. Then we studied the electrocatalysis of 4-nitrophenol over glassy carbon modified electrodes. Glassy carbon was found to be inactive towards 4-nitrophenol, and cobalt modification resulted in 2 peaks in the cyclic voltammetry. But the peaks are found to be less intense, but the cobalt oxide graphene modified GCE shows drastic response in CV, and the peaks corresponds to irreversible reduction of 4-nitrophenol to para-hydroxyaminophenol, and there is a redox couple of para-hydroxyaminophenol 4-nitrophenol 2. The reactions are shown here. We didn't study the electron transfer reactions now, but we have to do that also. There are 2 kinds of reactions. One is the irreversible for electron reduction and a 2-electron redox couple. In order to study the nature of the electrocatalysis over cobalt oxide graphene modified glassy carbon electrode, we have analyzed the CV at different scan rates. And it can be seen that there is a slight shift for the redox peak. There is a slight shift towards the of the EV value towards right or for the oxidation reaction and towards left for the reduction reaction. This is an indication for the quasi-reversible nature of the process. And in order to check the nature of the electrocatalysis, we plotted current versus square root of scan rate, and we are getting a straight line, and this indicates that the electrocatalysis of 4-nitrophenol over present nanocomposite is a diffusion control process. This is displayed for both oxidation as well as reduction reactions. And the major conclusions are, we have presented a facile green liquid phase exfoliation of graphite using ethyl cellulose. Solar thermal assisted method is used here for the successful fabrication of CO3 over graphene nanocomposite. The material characterization studies reveal the formation of a hybrid nanocomposite with well-dispersed CO3 over nanoparticles over graphene sheets. The electrocatalytic properties of the nanocomposite towards 4-nitrophenol is investigated using cyclic voltammetric measurements. The hybrid nanocomposite showed outstanding sensitivity towards 4-nitrophenol when compared to their CO3 offer. We didn't study the response of pure graphene because the yield of the graphene after calcination at 400 degrees Celsius was very low. The electrocatalysis reaction, there occurred an irreversible reduction of 4-nitrophenol to 4-hydroxyaminophenol and a redox couple of 4-hydroxyaminophenol to 4-nitrophenol over CO3 over graphene modified glassy carbon electrode. The linear plots of peak current versus square root of scan rates indicates diffusion controlled electrocatalysis of 4-nitrophenol over the nanocomposite. So in conclusion, we can successfully report a liquid phase exfoliation of graphite using ethyl cellulose as an exfoliating agent, and we could produce a nanocomposite of CO3 offer with this graphene, and it can be applied for other applications such as for pollutant degradation, drug delivery, etc. This work is mainly done by my student Anila Das during her MSc project work. And the work is not complete. We have to further characterize the CO3 over graphene nanocomposites using Raman spectral analysis, XPS, etc. to prove a defunctionalization and less defective nature of the graphene. And we have also have to extend the application towards the sensing behavior of the modified electrode towards 4-nitrophenol. We have to study the linear range, selectivity, and sensitivity in the sensing of 4-nitrophenol. And we also have to analyze real samples where 4-nitrophenol comes as a pollutant. These are some of the references. I would like to acknowledge our college, Sree Neelakanta Sanskrit College, Pattambi, former and present principals of our college, head of the department, Dr. P. Venugopalan, and all other faculty members of the Department of Chemistry for their support. Our analysis is mainly done at SAFE CUSAT Cochin. And I would like to acknowledge my student Vijayasri Haridas, UGC JRF, because she has started electrochemical studies in our group for the first time. And the funding agencies such as DST, New Delhi, India for FIST program, CSIR New Delhi, India for EMR project, UGC. And I also would like to acknowledge the University of Calicut, which our college is affiliated. This is my research group. On the top, the students who are currently doing PhD is shown, and in the bottom, those who have completed their PhD. And on UGC postdoctoral fellow was also working with us, Dr. Silja PT. Thank you all.
Thank you, ma'am, for a nice presentation. Now the session is open for discussion.
It is, let me ask one question. It is indeed a great pleasure to see that people are in a position to do research in colleges, and you are, I can imagine the kind of troubles you would have gone through to get all this data and to get these things completed in a reasonable time so that the student could graduate and go away with their MSc degree. So thank you.
Sir.
You know, this is a motivation. Let me ask you about this particular system, the cellulose that you have chosen. What specific advantage did you get by this exfoliation method as far as graphite, graphene, and its properties are concerned in comparison to other methods?
Okay, thank you, sir. Actually, I'm not in a position to completely explain this thing because we have to analyze more. But specifically, I can say that we could produce a high quality or less defective graphene by this method. It is highly advantageous. And ethyl cellulose is a perfectly green material, so there won't be any contamination while use or while during its applications. So our target is mainly to produce less defective graphene with high conductivity. This will help as well as with a high electron mobility. This will be definitely helpful during electrochemical studies.
If you were to look at, you know, there are several other methods, as you mentioned, but this methodology, because it is food grade material, are there some specific application possibilities that you are thinking of using graphene derived from cellulosic methodologies?
Actually, we think that we have already produced graphene oxide, graphene ethyl cellulose nanocomposites too. These materials can be used for drug delivery as well as controlled drug release. These kinds of composites can be used. Excluding the metal oxide, the graphene ethyl cellulose nanocomposite, we could produce some microspherical capsules of ethyl cellulose within graphene layers. And these kinds of materials can be used in drug delivery as well as drug release, controlled drug release.
Very good. Thank you.
Dr. Binitha, can I ask a question?
Thank you, sir. Can please ask?
I am Mujib.
Okay, sir.
Have you checked any medical property or drug delivery property, or have any idea?
Actually, with the ethyl cellulose, we just studied the controlled release of paracetamol. We just studied during one of our BSc project work. With ethyl cellulose alone, we already studied. It is just an in vitro study, not in vivo.
Okay. Has it any edge over other methods?
Pardon, sir?
Is it having any advantage over other methods?
Ethyl cellulose is already used in drug release formulations.
Is this more effective?
For paracetamol, the controlled release is highly important because excess dosage will cause us even liver damage. So if we can use some controlled release of paracetamol, it will be highly beneficial. So ethyl cellulose is a perfectly green material. It is already used in drug formulations. But in our method, those are microspherical ethyl cellulose. But here we could produce even submicrospherical capsules of ethyl cellulose wrapped with graphene sheets.
Okay, thank you.
Okay, sir.
Okay,
Thank you.
thank you. Congratulations for the work.
Thank you, sir.
Question. Okay. Binitha ma'am discussed the synthesis of graphene by grain root using ethyl cellulose as exfoliating agent, and the metal oxide graphene nanocomposite by sorbothermal method, and discuss its electrochemical applications in a simple and effective way. Thank you, ma'am, for your valuable presentation.
Thank you.